welcome everyone and point out that we have a really talented group of people here today. There are actually really 30 different companies who RSVP'd, so I think it's really impressive the diversity of the group that we have. Although only a portion of folks are using ASDK, I think it's really interesting and important to note that we all face really similar challenges as developers. And it doesn't much matter how we tackle them as long as we all communicate and share ideas on our latest techniques. So why am I talking to you at all? I've dedicated my career to working on improving the quality of mobile experiences. I've worked on iOS and Facebook and Instagram and Pinterest and a couple smaller apps as well. But really, I want to work with people to try to bring the perspective of building high-quality user experiences as far as possible to the smallest applications. Most recently, I founded the core experience team here at Pinterest, and it encompasses web, Android, and iOS, and its charter is in fact this idea of quality user experiences and figuring out how we can achieve that from both a developer and a design perspective. So we have a lot of content today, and I ask you to bear with me because it's all come together quite quickly. I wanted to start out with a couple thoughts on what we do as a profession. It's really impressive that we take machines and imbue them with information, interactivity, and motion. These grant astounding capabilities to people in many different parts of society, and they really are changing the lives of an unfathomable number of people. I mean, really take just a moment to think about how many people are impacted by mobile devices, and it's impossible to truly conceive of it. Their impact is permanent, and it's also accelerating. And not only are these devices important to people, but they're also very personal. They're very close to people. They're within arm's reach of this truly tremendous number of individuals. So clearly, this heavy responsibility is felt by most of us here. And we feel a camaraderie from the type of challenges that we all face in programming for these devices. And this intuitive relationship that we feel when we work on these projects is due to that pursuit and that passion in trying to achieve something that's great. And so we should be proud of that, and we should do great work. So why is it that we don't always do great work, and why does it take so long to actually do so? I believe that there are common challenges that we end up spending the majority of our time on, and this limits our focus on things that are novel and things that are great. So my thesis is that these challenges exist because our abstraction layer, the APIs that we work with, is not expressive enough to obviate the complexities of these challenges. We have to speak at a language that has to directly confront the same challenges over and over again. So what are these issues? A lot of them will be familiar to people. This is not a definitive list, but there are a few categories that these tend to fit within. I want you to remember that there are developers around the world who have very similar challenges. We are in Silicon Valley, and it's easy to forget that a vast majority of both developers and users are not in the United States. So starting with layout, every single user interface requires layout, and it's quite a complicated problem. It's a very general problem. There are an infinite variety of layouts, and so it's a very important one for us to solve as optimally as we can. So a good solution would support scalability and would work for international audiences. It would control complexity of large layouts and make them tractable to understand. It would not have duplication in terms of similar logic that must line up in different parts of the code base. It would have user interface consistency in different parts of an application that are designed to be the same. And it would have natural transitions that can demonstrate to users why things are in different places and when they move. So with UIKit, there are a couple primary options. It's pretty difficult to do anything other than use one of these options, so most of us do use one of them. That said, both of them have really fundamental challenges. And I know all of us have used both of these before, so we won't go into it in depth, but manual layout is very duplicative. You need to have a sizing method and a layout method that are in different places but have to line up. This makes them very difficult to change. They're verbose. There's a lot of low-level math, basically, that needs to be done. They're stateful, which makes them error-prone because they can be interdependent on other parts of the interface. And they're not reusable. You can't take a template and apply it to other areas of the app. And they're also run on the main thread, which is not great for performance. And so what this basically looks like is a huge amount of code, and the code is very rote, and it will even give people RSI, how much code they need to type. So this is really not a good use of time, and it's not making your app great. Now, auto layout is actually a lot better in a number of ways, but it is worse in others. It has exponential performance, but it also has exponential complexity from a developer perspective as layouts get very large. Storyboards mean that your issues with a layout may not even exist in code, which makes them very difficult to debug, especially for more complex layouts. And just like manual layout, they are still not reusable, and they're still run on the main thread. And so in a nutshell, if you compare auto layout to manual layout, you realize that it's actually not even usable by larger applications. So we're forced to write pages and pages of code. So loading is another systemic challenge in our applications. These apps handle a huge amount of information, and it must consistently get it at the right time. Otherwise, people are left waiting. And if you multiply that waiting across the planet, it is truly staggering the amount of impact that it has. Nothing is automatic with most operating systems, even image loading, which is really, really surprising. And it's not just this idea of loading. It's downloading, it's caching, it's preparing things. And it's not just about performance either. It's about how much work it requires to take care of these rote responsibilities. And so what ends up happening is that different apps, all of our apps, have different areas that they don't do well. For example, it's very common to see apps that don't even begin loading images until they are already visible, which is especially awful for people on non-Wi-Fi connections. And reaching the end of content is also a common issue that loses all scroll momentum and really interferes with the user's flow with an app. So interaction. Clearly these devices are really small, and yet they provide access to a huge amount of data. So it's very important that users be able to navigate easily through this information. So of course we all try to achieve 60 frames per second. We all try to achieve low touch latency. And we have to write navigation patterns and controllers to encapsulate our UI and allow people to navigate between them. And there are also complex data sources to load infinite scrollable regions. Dealing with all of these things is really, really quite difficult. And so often we end up with something that is very jerky, that is very not pleasant to use. And it results in a lot of complexity for the user, for the developer as well, when they have to maintain these navigation patterns. So velocity is one of the most important aspects of what we do, because it's what determines how much focus we can apply to areas that are novel and interesting. We work with a black box system with iOS. It's one of the best systems in the world, but nonetheless, it's quite closed. And to be able to extend it is quite challenging. So if you want to add some basic capability to the system, you have categories, but that's just about it. There's not much that you can do. And if something's going wrong in the framework, you can't really see what it is, and it's tough to debug. New APIs may be released and they can have quite good functionality, but you can't truly rely on them. It's not that big of a deal to adopt a new API and have it as an option, but if you can't rely on it, then it doesn't really have an impact and allow you to simplify your application. And there are also behavior changes that are unexpected, that are not documented, that are even difficult to discover and even more difficult to deal with. Of course, these frameworks are often very sensitive to small errors and can cause stability problems. And so we've all seen things like this, where we literally re-implement an operating system feature because it was introduced on a certain version, and we have to support a prior version. And this is not an isolated case. This happens all the time. And so fundamentally, developer velocity relates to resolving problems that already have good solutions. There is no standard UIKit extensions framework. And sharing a single great idea often requires launching an entire open source project. So what this results in is that large teams rebuild the wheel. They create their own internal framework. And in fact, in your career, you may work on more than one application that has a different internal framework, and you may end up re-implementing things in more than one internal framework. Small teams end up stressfully working through issues one at a time, build up their own internal framework, which is often more clean and functional than some of the larger ones, but nonetheless are distracted by this. And ultimately, the best that we have are a bunch of dependencies. Which is great that this does help. It helps quite a bit compared to solving things yourself every time. But again, the fact that you have to launch an entire project means that people aren't able to easily share what they come up with. So let's take a moment to think about what I mentioned at the beginning, which is how the layer of abstraction that we're working at relates to this. So I take a lot of inspiration from the profession of architecture, and it's very interesting and I think very important to take some lessons from it. Architecture is defined as, or there are several definitions, but it includes knowledge of art, science, technology, and humanity. It is both the process and the product of planning, designing, and constructing systems. The design activity of an architect is across both macro-level and micro-level concerns. The practice also encompasses pragmatic considerations, including scheduling, cost estimation, administration. The documentation produced by architects defines the structure of the system that is being constructed or has been constructed. So there's an interesting quote from literally 15 BC that a good architect provides all three: firmness, commodity, and delight. An equivalent today might be durability, utility, and aesthetics, but nonetheless, the idea that it is the responsibility of an individual with this profession to provide this diverse range of goals and to trade off between them is very important to our work as well. Lastly, it is important to remember that the notion of architecture, and in our field as well, applies to both design stage and construction stage. And so what I believe this means is that architecture is a combination of design and engineering. I think that's the same thing for building mobile apps. So what can we learn from this profession? The principal tool of the architect, as well as the engineer, is abstraction. High-quality abstractions are required to produce large, novel systems. And furthermore, the quality of those abstractions limit the systems that can be produced by any group of people of any size. And high-level abstractions allow focus on the bigger picture and allow focus on taking the next step to build something that's more important. So what are today's abstraction layers? We all know about this, but these layers are quite old. You know, hardware has evolved dramatically, but the fundamental principles of it were established in the 1960s. Operating systems have also evolved, but again, their fundamental principles have been static essentially since the 1980s. Languages, we all know that Swift is evolving, but the fundamental principles of our languages have also been static since around the late 80s to 90s with object-oriented programming. And indeed, even the core frameworks of Foundation, core animation were essentially finished in the 2000s. Now, the higher level app SDKs are still evolving. On our platform, created originally in 2007, but they have slowed down in how much they are changing, and their biggest advancements occurred back in around 2012. And so I believe that we need to collectively produce another layer of abstraction. Indeed, this can be seen in the industry with a few different frameworks attempting to do this. But I draw this relatively rote picture because it's very important to understand this as a separate layer of abstraction and for us to design APIs with this perspective in mind. So what would it take to define what a layer 7 abstraction is, or an abstraction layer? Let's dive right into it. As with any layer of abstraction, the layer should be able to offer principles that help solve the challenges of the layer beneath it. It needs to be comprehensive enough to allow developers to have a fundamentally improved mental model that frees them from the everyday constraints or everyday considerations of the lower layer. So I believe that a properly designed level 7 framework would be the closest that we have yet come to matching the human intuition of how apps work. And this is very similar as well to how physical objects work. These abstractions should be able to express macro-level user experience concepts rather than micro-level user interface operations. Industry consensus appears to be forming that declarative UI and declarative data management is part of the solution. There are several frameworks who have explored it, but there are very different approaches to how that piece is integrated, and it is only one small piece of a framework at this layer. So what is AsyncDisplayKit's approach to attempting to evolve a layer 7 API? The first is to have intelligent behavior in components of various levels of abstraction. So in other words, to have objects that you can rely on to behave in a way that is desirable, that you can, for lack of a better word, trust to take care of a lot of the normal responsibilities of UIKit management. AsyncDisplayKit has evolved into a fundamental design pattern relying on a hybrid declarative model that helps encapsulate the intent of what developers want to do rather than codifying it as instructions. It needs to have an open platform because this is what allows developers to rely on new functionality and new ways of doing things and to participate in improving them and to drive the approach forward much more quickly. And it should enhance the operating system. It should tightly integrate with layer 6, not obscure it completely. And one of the reasons this is extremely important is that we have not yet, as an industry, figured out what is the perfect approach to this layer of abstraction. This is a fundamental difference about how AsyncDisplayKit is approaching this problem, whereas most other frameworks today take the approach of completely abstracting away layer 6 from the developer. So what are intelligent behaviors? It's the idea that our mental model should be working with real objects. You do not ask a real object to load. You do not have to manage its state. And dealing with an object does not cause your worldview to drop a frame. So this involves a few different things. Physical life cycles. In other words, objects are persistent and continue to exist. And therefore, you can put state in them that will live as long as it makes sense for the user. Intelligent preloading, a context-sensitive way to load their data. This also includes logging, so visibility events and so forth, and dealing with performance considerations automatically so that you can interact with objects without fear of impact on the rest of your application. So AsyncDisplayKit has always supported intelligent preloading, but what we've added with version 2 is multi-dimensional preloading. And so we do network loading. You know, content comes in from off the screen, we load from the network, we trigger displays, and these objects know when they are visible. And as they leave this area, they also purge memory, but they remember that they are the same objects. And so even when there is a different dimension or a different way of interacting with the content, it's still important that these objects behave in a realistic way. And so these preloading mechanics work in other dimensions as well. And it turns out that this is also implemented to work across navigations so that you can open content and have what you could call three-dimensional preloading. So it is truly a multi-dimensional or n-dimensional implementation. So hybrid declarative UI. This is not a definitive term by any means, but is meant to differentiate it from a pure declarative approach. The perspective is that imperative styles are important to user interface programming, and we should not completely eliminate them. Instead, we should try to automate imperative UI as much as possible by using declarative specification without preventing users from doing imperative operations seamlessly. So what are the benefits of this? The simplicity of declarative specification is very important. It allows reusability and composition, but it also controls complexity of very large software systems. It allows the level of fine-grained control over components and behavior that imperative specification does. And it also supports this high-level notion of developers being able to transition between multiple states in an interface and controlling how those transitions behave, as well as supporting different modes of an interface to be able to very easily experiment with different looks for the UI when prototyping or with experimentation in the wild. So what does this actually do? The key API in AsyncDisplayKit is automatically manages subnodes. What this means is that the layout then specifies what is actually in the hierarchy. This automates commands like add subview in AsyncDisplayKit, add subnode, and removing them as well, so that your code can very easily say what should exist in the hierarchy, where it should be, all in one expression. Now, these are very basic transitions. I'm very thankful that Michael built this in about an hour. And nonetheless, the code to drive them is extremely simple, and it is extremely customizable and very extensible. And so this is what we mean by a hybrid declarative UI that allows the developer to dive in and to have more nuanced control when needed. So an open platform. This is very important for a Layer 7 framework to evolve at a pace that is not on the scale of decades. And I don't think any of us are interested in waiting for that. It, again, allows people to rely on those new abstractions. It automates compatibility with different iOS versions because you can share observations about compatibility issues with different versions and bake those into that layer of abstraction. And you can benefit from a long period of time of intense development of many developers because the framework is open. It has a long life cycle and many people engage with it over that life cycle. That means that the generalized solutions within it can improve over time, and we can start with something that is useful and make it truly indispensable as the right abstractions are created. And lastly, it can also allow people to share individual conveniences that make their development lives easier, even if they're not worth launching an entire project for. And lastly is the notion that AsyncDisplayKit should enhance the operating system and not hide it. We believe that apps should be able to mix and match ASDK and UIKit smoothly, that they should be able to write only one view in their application with this framework if they choose, and that the APIs should be as familiar as possible, indeed identical, wherever that makes sense. There should never be arbitrary divergence, and we should support forward compatibility by relying on the operating system principles as closely as possible so that even as something like tvOS comes out, AsyncDisplayKit can continue to support it. So let's talk about some of the implementation details of this. These are some of the most core concepts of the lower levels of implementing this layer. We have the node, which is a higher order version of a view. We have the layout spec, which is an encapsulation of the idea of a layout. And then we have the element tree, which is how nodes and layout specs work together. So a node is a lightweight, long-lived, intelligent, and concurrent version of a view. The node can exist without a view, which is what allows it to be lightweight. It's long-lived because it's lightweight and can be kept in memory in the numbers of hundreds of thousands without creating memory problems. And that means that state can be kept in nodes for long periods of time without worrying about having to reuse them. They're intelligent, so they implement the characteristics we talked about earlier. This means that not only do they manage their view and layer in the best way they know how, but they have context about their state and their position in the interface and how it changes over time. And so when a node needs to be displayed, it can create its view, or as an optimization, we can also just create a layer. So the last one is a bit more interesting, and that's concurrent. Nodes are fundamentally thread safe and have many different behaviors that can be performed off the main thread, creating, measuring, laying them out, as well as displaying them. And each of these not only utilize all CPU cores, but avoid being run on the main thread. To understand how this looks in practice, the video we saw earlier of a stuttering app involves a main thread that is congested at the moment that a new frame needs to be drawn. With AsyncDisplayKit, when scrolling is occurring, there are ample gaps within the main thread to process the user's gesture immediately, and we use background threads to run ahead and load as much data as possible. So the layout spec. This is a unified, declarative, reusable, and also concurrent abstraction. Looking at its definition briefly, we can see that it is an NS object just like a display node, and they both conform to a protocol called ASLayoutElement. And so a layout spec has children which are ASLayoutElements. So the traits of a layout spec are, again, that it's declarative. It represents only the idea of a layout. It has no physical presence. It does not depend on any specific frame value. And it also, again, has children that are either other layouts or nodes directly. The role is to abstract layout out of nodes, which is like taking layout out of views. This is very important because it also relates to auto layout. Not only is it like removing the layout subviews from a view, but it's like removing the auto layout constraints from the view as well. The layout spec can then encapsulate the math details of how to compute a layout, and is generalized to act on other layouts as well. So what does it actually do? When provided a size constraint, it can then, knowing its context, calculate the specific frame values for all of its children, and then it can also understand what its own size is. As a result, nodes can adopt layout specs as their delegate to entrust them with the responsibility of positioning all of their own subnodes. So the most important element of this term declarative that we've been talking about is how easy it makes it to compose different types of elements. So these are the built-in layout specs. A few hand-drawn examples give you a sense of a few of the parameters they can control. The most powerful by far is the stack. But let's walk through a very quick example to show you how this works. So building a pin node, we start with a layout spec method with a vertical stack. We give it a spacing, and we give it some children. And so we end up with these 3 blue rectangles on the right. So that's not quite good enough, and so we want the image to be taller. So we could specify on the image node that it prefers a certain size. That will make it its size, but this is really a hack. We don't want to actually have any hard-coded logic here. And so another way to do this would be to provide a ratio and to encapsulate the image node with a ratio to make it 1.0. This allows the node to express what it wants about the size that it desires, but if it has no preference, it will fit what the parent is providing while matching that ratio. So here we can see the first element of nesting and composition. So we also want to provide an inset to the items at the bottom. So we can create an inset spec to apply that as well, but the question becomes, what is the child of the inset spec? It's simple to then create another vertical stack, which can contain the 2 elements that belong in the inset. And that results in a layout much like what's above, where the final stack contains the ratio spec containing the image, and we can also take in the inset stack as the other child. So the element tree, how does this actually result in computing frame values? So this protocol I mentioned earlier, ASLayoutElement, implements a method for you called layoutThatFits. And this returns objects that represent the specific size and position of a given layout element. So once this has been generated, once you call layoutThatFits, the resulting layout is both aware of the element that it is the layout for, as well as that element is aware of the layout that represents its size and position. These layouts are then cached as long as they can be. So layout objects are hierarchical, just like the layout elements that they represent. They define the frames of every subnode of elements in a tree, and they're used, again, they're reused in the next layout pass. So let's walk through an example of measuring the pin node that we just built. We provide a layout spec by layout spec that fits, and it looks like this. The dark blue are layout specs. Remember, everything here is a layout element. The dark blue are instructions and ideas about what layout should be performed. They don't have any concrete representation, but they are acting on concrete objects. Nodes, as we'll remember, have context on where they are in the interface. They know how to load themselves. They know what size they would like to be. In the case of the count node, which knows its own font, it knows its own text as well. And these other specs represent instructions about how to position those. And so when we run the measurement pass, we call on the root of this tree that we saw earlier, layout that fits. And that produces a tree of AS layouts, which represent a specific computation of the layout. Lastly, we flatten the layout to remove any of the layouts that only correspond to layout specs, because those specs have no visual presence in the resulting UI and therefore aren't needed. And lastly, we cache the layout by linking it to the layout elements it corresponds to. Broken out a little bit more, it's interesting to note that, of course, the sub-layouts also relate to the subnodes of the node as well. And so even if parts of the tree change, parts of the layout can still be reused without being recomputed. So the other part of this, having completed the measurement pass, is the layout pass. The most critical thing to observe here is that this eliminates duplication between what in manual layout you would implement as size for item and layout, because this method is completely automated. In fact, not only is it able to apply the frames to all of their corresponding objects without the user even writing this code because it's in the framework, there is also logic that understands that if there is an element in the layout that is not currently in the hierarchy, it can simply add it for us. So how does this set of principles and implementation actually address the challenges that we talked about earlier? Running through these at a high level, the layout challenges we saw, such as having duplicated logic, can be unified by this layout spec concept. Stateful layout becomes declarative and does not depend on elements outside of the layout spec method. Storyboards are no longer a static piece of instruction that exists outside the code, but rather the code defines how the layout performs. Automatic hierarchy management removes the possibility of issues where you can leave a view in the hierarchy too long or something can jump out of the hierarchy at the wrong time. It's completely open, so you can track exactly where specific values are coming from by reading the source code rather than guessing based on input values to the framework. It's reusable because you have these layouts as templates, and it's very fast, so you can prepare all of these layouts without ever touching the main thread. So loading is addressed by the intelligent behaviors we talked about. In fact, all of these things, downloading, caching, and preparing information are automated, and not only these basics, but advanced stuff also comes for free. So all of these loading behaviors adjust to the context of what the user is doing and try to be only minimally aggressive at using data. They act in multiple dimensions. There is dynamic download priority depending on how close an element is to the screen, and memory is managed proactively so that memory warnings don't occur. And it supports a variety of formats as first class, so not only progressive JPEG, but also animated GIFs are supported directly in the framework, and JSON batch fetches from the server are also triggered by the framework. And attributed strings have very deep support, such as even having text attachments that themselves are asynchronously decoded images that are inline and flowed throughout the text layout. So the interaction challenges we discussed, 60 FPS and 50 milliseconds often is achieved without optimization. This is because there are a variety of optimizations in the framework that are possible only because this layer exists within which those optimizations can be contained without application code being concerned with them. This includes concurrent layout and rendering, but also run-loop impact distribution, which is an interesting technique that allows us to minimize the effect of work that does have to occur on the main thread and is very difficult to implement manually in a regular application. The internal core of AsyncDisplayKit is almost entirely Objective-C++ to reduce even method dispatch and memory allocation overheads. And there are also special optimization features that you can opt into if you need further optimization. Now, we've also seen that navigation controllers and view controllers can become very large and very difficult to work with. That is addressed in part because by relying on the behaviors of individual components, the logic that's often within view controllers can be removed entirely and pushed down to the components themselves, which also reduces duplication across multiple types of controllers. And finally, collections and tables. We've all seen the internal inconsistency exception, and this is an area that we are very actively working with a new API that should be able to bring the declarative approach to data sources as well as to layouts. So developer velocity. Extensibility, being able to add features directly to the base classes is tremendously powerful. Debugging through framework code allows developers to move more quickly. New APIs that are added either by yourself or by the framework are immediately available on all operating system versions, even the oldest ones. Behavior changes that exist in many layers of iOS can be isolated by the framework by putting the awareness of those behavior changes within the framework and making them consistent at the framework API layer. And stability can be improved as well by having more tolerant base cases for common mistakes, as well as giving more detailed information about why those errors are occurring so that you can fix them faster. And lastly, developer velocity is improved by the convenience of many small additions to the framework. For example, by flipping on to debug options, you can get a sense of what areas of your interface are tappable, whether or not they're large enough, whether or not they overlap, whether or not you're downloading too much image data and are downsampling it or upsampling it. And these type of features are easy to add in an hour by working on one of the base components, and as a result, we have on the order of a dozen features like this that are meant to improve how quickly developers can work. Finally, I wanted to give you a quick overview of what it's like to design at this layer and build an application. We won't go into much detail on how the app was built, but I do want to discuss a bit about what recently launched as a renovated version of Pinterest. Our goals for Project ABBA, as it was known internally, were great performance, rapid iteration for developers, and most importantly, the first version of features should be as high quality as possible without a big gap between when a feature could first be shipped and when it was truly polished. And from the design perspective, we wanted things to feel more dynamic and more interactive than the previous app, to be scalable across devices, as many new device types were launching around this time and becoming popular, and to be consistent from a design rule perspective across different features, including new ones as they were implemented. So this leads to an architecture conclusion that we must build in the design system so that developers don't need to do additional work to conform to it. The components should be truly self-contained as much as possible, and those components need to be fast by default or we wouldn't be able to achieve great performance. So Pinterest is a very complex app, and here you can actually see that there are three dimensions that the user can travel within. They can scroll vertically, they can scroll horizontally, they can open content, and that content can also scroll in both directions. And so we wanted to make it possible to work within this context to rapidly change features without creating regressions and without both in terms of performance but also in terms of the functionality of the app. So some of the issues with the code base at the time, auto layout performance was a serious challenge. Content loading and caching was inconsistent around the app. It's very difficult to do consistently in an app of this size. The design had many small inconsistencies throughout the app, despite the best efforts of the team. And the code complexity as well as reuse issues were just very difficult to avoid with a growing team of people. So it's really important to start with a design solution to developing an app at this layer of abstraction. And as we discussed earlier, great apps have to be a combination between engineers and design, working as though they share a profession together. So briefly, and this is what I believe is the most important takeaway in what comprises building at layer 7, I will overview what our team came up with as their core principles, the laws of physics as they were for our design system, the components we provide, and compositions of those components. So our core belief, of course, was that there needed to be one system to handle all of our UI, and the design principles were that it should be interactive, it should encourage people to explore, it should feel more like a toy than a machine, and it should be device independent in its scalability. It had to have absolutely first-class internationalization and be truly customized for each locale that it shipped in. And the design system needed to have standardized components that had a consistent way of referring to them and a consistent language. And so the system basics include choosing a set of colors that can be exposed as their meaning in the application rather than their color code. A lot of effort was spent on typography to choose not only the font sizes, but to make a mapping between meaning of the font. In other words, is it a text body or is it a display header? And the size of the text within that category and the type of device that it operates on. And so a given developer will choose whether they have regular text or a display header, and they will select, based on what the design specifies, a size. And so never is a font size required in the code, and this allows us to scale the sizes even according to user preferences like accessibility. There are many other reasons the typography system had to be tabularized in this way. There are, for example, adjustments to the tracking or word spacing and other special typography features that had to be built into AsyncDisplayKit to even support what the design team wanted to do. For example, there is a transformation applied to all character-based languages to make sure that they read properly to those users so that they feel right in tone. What we found is that using the same size, a huge number of users in those locales felt too bold. It felt almost rude and like yelling or like uppercase. And so applying a transformation to these fonts in the framework layer was the only way to support this kind of behavior. And so the result can be seen here. These sizes are specified identically on these two devices, but are different in their result. Of course, we needed to come up with an iconography set, and our icons, I'm very happy to say, had the benefit of working with Susan Kerr, the designer of the icons for the original Mac. It was a great pleasure working with her on this project. We came up with a grid system that allowed us to take any number of objects in terms of a stride on a screen of any size and fit them in a certain number of columns, that these columns could then be varied depending on the gutter widths or the size of the item desired. And that would allow us to set our componentry on that grid. And lastly, we came up with what is called the Brio point or point, which is sort of like a scalable point. So if you have something, these are scaled to look like the same size image, but actually occur on a small iPhone, a large iPhone, and an iPad. And the correct font size for the varying image sizes is different, but also so is the amount of space desired between components, both vertically and horizontally. And so all of our designs are specified in a more abstract unit and then adapted on the device. So the independence and intelligence of objects is fundamental to our implementation approach, but it is also to our interface approach. And so we have a bunch of different object types, of course. Let's look very briefly at boards. This is an example of what a board can look like in different contexts. From a developer perspective, these being design considerations and details, these are all the same component that understands what environment it's in and understands what display it should have. There are a limited number of customizations for whether it should be large, medium, small, etc. And lastly, these components fit within layouts. And so a layout, can be the actual screens that users see. And so we, of course, want to make these layouts as much as possible be collections of the components. Here are a few more. So the outcomes were some success at building in the design system. I encourage you to look at some of the engineering blog posts that have been done on this topic. Both Garrett Moon and Ricky Cancro did a great job of describing some of the details of implementing the system. To have self-contained components that would be able to load themselves and to have dramatically improved performance. The design system is implemented, for example, with a layout spec that understands that multi-column grid and then can align items to it. The scalable points are implemented in the layout spec layer as well as the core components. And because these rules, including how text should be inset and so forth, are implicit to the components, the developer does not need to write any code whatsoever to trigger them, and that is the only way to achieve consistency. Cool, so comparing launch time, we achieved a significantly faster launch for loading fresh data. On the right, the old app is still showing cache data, and then eventually the full data will load. But in addition to a much faster launch time of between 2 and 3x, the user interaction performance of dropped frames and latency were improved by a full order of magnitude. So with that, I want to invite up Garrett Moon, who is one of the most experienced developers at Pinterest and who has recently stepped up as the engineering manager of the iOS frameworks team, including AsyncDisplayKit.
Thanks, Scott. So yeah, I want to talk about the future of AsyncDisplayKit. It's that button. Okay, not the laser button. So first I want to talk about open development. Throughout development of AsyncDisplayKit 2 here at Pinterest, we continually merged in AsyncDisplayKit Master into Pinterest Master, which was good and bad, but mostly good. We've had bugs found by community members before they got shipped out to Pinterest. In fact, we had a bug submitted by Buffer that would have been very, very bad if it went out. And we've, to be completely frank, done the other side too. We've had ASDK bugs that we found before they got shipped out widely in ASDK releases. So there's been a big mutual benefit to working off ASDK Master. And we've also used this opportunity to get huge amounts of feedback, internal and external, for new APIs that has been invaluable in shaping what ASDK 2 has become. But we want to get better. We want to do more open development. 2.0 was announced as coming soon back in 2015, so there's been a little bit of feature creep. And in the future, we want to be scheduling releases and really evaluating whether the features will be complete in time before including them in a milestone. Because there will always be a next release, obviously, and we'd like to have branches for every dot release and every release so that we can have bug fix releases a lot easier without including new features. Because right now we have to tell people, maybe try out the new features because your bug is fixed over there. And we want to actually do this all more publicly as well. So currently, Pinterest has an internal bug tooling Jira, but the frameworks team is going to be using GitHub issues to do all our issue tracking so that we can do it in public. And we also want to be doing our road mapping in public as well. So we'll be look at GitHub milestones and you'll see what we'll be working on for the next dot release and the next major release. So we're going to get much better at that, and I encourage you to go take a look. Next, I want to talk about what we can build together. There's still a lot to do in AsyncDisplayKit. There's still a bunch of things that we can do to make it better. And the first category I want to talk about, these are just some ideas. We're working on some of them, and we want your help. So I'm talking about other ones that we're not working on yet. But we want to start with better debugging tools because ASDK can be hard to work with sometimes. It's gotten way better in 2.0, and we want to make it better still. So imagine a tool that would allow you to override set framer bounds. So I don't know how many of you have been working with ASDK and been like, how the hell did that node get there on the screen? And you can override set bounds or set frame on the node, and it may never be called because it was set directly on the layer or directly on the view. So we could build a tool that allowed you to basically make sure you knew when that was actually getting set. We could build a visual layout inspector. So we have all these new cool layout specs, and we actually have a cool tool for inspecting them, which is an ASCII art string. Any layoutable element, as Scott mentioned, which is a node or a AS layout spec, you can call ASCII art string, and it'll give you a little art string. But imagine one that like you could interactively turn on a mode in your app, tap on a node, and it would give its layout tree visually. So you could see, just like we had on the slides, something like that. And we want to build more asserts earlier. So this is basically catching problems at the time they occur. So a good example of this is we had a bug in Pinterest where we would get crashes on layout because there was invalid layouts occurring. And we couldn't figure out, okay, who set this invalid layout? What caused this invalid layout? And it turned out that there was a preferred size set on a node that didn't make any sense. And so putting an assert there when you actually set it on the node made it a lot easier to find those problems in the future. So we want to get more of those to make it easier for you to learn when you make mistakes and to move quickly. And another idea is event history, and this is another thing that's being worked on right now. Event history is the idea that you can add a macro in AsyncDisplay node that every time you call it, it logs an event, and it could be like visibility event, like did enter preload range, did exit preload range, and every time that's called, it actually records a stack trace as well. So when you're like, how did this happen? You can ask the node, what has happened to you in your lifetime? And you can be like, oh, your visibility was set here, but when? And it would say it was from this thread, and it was at this time. So you get a full stack trace at the same time. So we can build tools like that. We want to improve automatic behaviors. So currently we have something called automatic subnode management, but it's opt-in, and it works with layout specs. But it would be great if we could just turn this on automatically for you, and all your nodes are inserted, removed from the hierarchy. Doesn't matter what your animations are. It all just happens magically. Automatic layer backing. So we talked about how nodes as an optimization, you can have them be layer backed. But the problem with that is if you want to do any touch handling, layers don't support touch handling and you need a view. We could potentially detect that based on if it's an AS control node and you've added a target, then you can't be a layer. But if you haven't, then you can be a layer. So we could do that optimization for you potentially. Another idea is RTL support for layout specs. So that should be pretty simple, right? We're just basically flipping them back and forth. That's famous last words, of course. But imagine you could just flip all the layout specs, but you could opt out on some of the layout specs so they wouldn't flip because you don't want to just flip everything. But that would give much easy support for international use cases like Arabic languages. And then truly asynchronous layout. So this is something we're working on. Currently, you can get asynchronous layout, but it's another thing that you have to do yourself. You have to call measure on a background thread, and then when layout comes in, it will use that cached result from the measurement. But what if instead, when your layer or your view had the layout is needed flag set on it, we kicked off an asynchronous task to measure for you, and then when layout came, if it wasn't done, we waited till it was done, and if it was, we just applied it. We could get truly asynchronous layout. And another thing we'd like to do is be more declarative. As we talked about, there's a lot of push towards declarative, and it's because it makes it a lot easier to solve problems quickly and to reduce the issues you might have with imperative programming. So as we mentioned, we're working on declarative data sources for tables and collections, where you just have to add a section and an item, or add sections and items, and manage your data source. And when your data source is updated, just call reload, and it does all the insertions and updates automatically for you, and you don't get crashes when you have differing numbers of items. And we also want way better support for Swift, because Swift is the future, and one good thing would be, for example, if SourceKit didn't crash when you were using ASDK with Xcode. And finally, I want to talk about kind of a bigger pie-in-the-sky idea, which is potentially making something like AsyncKit. We've seen that AsyncDisplayKit is kind of a Swiss Army knife. It's got a ton of different things. It's got a whole layout system and it's asynchronous rendering system. But it would be nice if you didn't have to adopt all of that at once, and you could just take the bit you wanted. Maybe you just like the layout system, that you can have this declarative layout. Maybe you really care about imperative programming, but you want to do all the asynchronous rendering on your own. So that's an idea we have as well. Next, I want to talk about contributions. As we mentioned, AsyncDisplayKit is very international. We took this a week and a half before Thanksgiving. This is basically the users coming from all over the world to the GitHub page. And we've had tons of 2.0 contributors, and I want to thank all the people here and everybody that took the time to report issues, because it's made the Pinterest app immeasurably better and also improved the open source community. And finally, I want to ask all of you to contribute. Connect on our Slack channel. We have that on the bottom. We have over 500 people already actively engaged on the Slack community. We want you to share your experiences there. We want you to improve documentation. It's really easy. You go to the documentation site. There's an edit button. You click edit. You edit the documentation, make it better, and submit a pull request. It's all very straightforward, and it's a great way to learn more about ASDK is writing documentation. Please write documentation. And next, we'd like you to contribute layout examples. We have layout examples. If you just go to the examples directory, there's examples there, so a great way to learn. And then, again, you can learn by writing more. And please contribute code. So if you have a feature idea and you want to build it, first step is submit an issue. We can all talk about it there, talk about the best way to implement it. And then, hell, you can submit a pull request, and we'll get it in there. And if you don't know what feature you want to build, there's tons of GitHub issues with needs volunteer label, so you can go submit that way. And finally, I want to announce tonight that we actually did push the release candidate for 2.0 this evening, about an hour and a half ago. So please go try it. You can just specify the branch in your pod file. And finally, we're not going to do a panel discussion because we're kind of running late, but I did want to recognize Michael and Adlai and Hannah and everybody on the team for all the hard work they did. They should stand up too so you can see who they are. I did that also, so now you can go harass them with questions since we can't do the panel discussion. So thank you all for coming. I really appreciate it. And yeah, if you have questions, we're here to answer them as best we can.